This z-test involves testing hypotheses about the population mean of a normal distribution when the standard deviation is known. And the first approach that we will take is what's called the standard critical value approach. In this approach, there are several different techniques that are commonly used to test hypotheses about the population mean of a normally distributed random variable. Now, the existence of these different techniques is due to differences in the assumptions of the tests, as well as differences in the decision criteria that the statistician wishes to use. The simplest of these methods is the standard critical value approach. Now, this approach assumes the data set is a random sample from a normal population with known standard deviation. And that's the important thing over here, this known standard deviation. If we have a normal population, but the standard deviation is unknown and has to be estimated from the data, we will not use the z-test, but instead we will use what's called student's t-test. Now, the rationale of the approach is based on assuming that the true population mean is some hypothesized value, which we symbolically note by mu naught. Now, this little subscript 0 can be read as naught, N-A-U-G-H-T, naught, or it can be read as mu sub 0 if you like. But the important thing is that this Greek letter mu represents the population mean, and the subscript 0 represents the idea that this population is hypothesized. That's the important word, hypothesized, under the null hypothesis. Now, with this assumption in place, we then have what statisticians call the null distribution. The null distribution is the probability distribution that we would expect, assuming that the null distribution is true. Implementing this assumption using the standard critical value approach is simple. Simply standardize using the value of the population mean that makes the null hypothesis true. We then collect data. We calculate the average, which we call the sample mean, and then we standardize this average using this hypothesized mean to get a z-value. If this observed z-value is too extreme, and extreme is defined by the alternative hypothesis, we reject the null hypothesis that the true population mean is as hypothesized. Now, how extreme is too extreme? The answer to this question depends on the significance level of the test, and as I mentioned before, the alternative hypothesis. Now, let's look at the logic of the standard critical value approach. Let's let X represent a normally distributed random variable, and let X bar represent the sample mean from the random sample. Hypothetically, let's just suppose that the true population mean is just some arbitrary value, which we are going to call mu naught or mu sub 0. So we're going to hypothesize that the expected value, that is the population mean, of the random variable is just some hypothesized value. But then what do? We standardize this sample mean under this assumption of the null hypothesis, and we use the standard error of the mean that comes from the known standard deviation. And this has to be given in the problem. This gives us a null distribution that follows a standard normal distribution. The third step in the logic of this is we simply reject the null hypothesis if the z-value is too extreme. Now, this depends on the significance level alpha, and it depends on the alternative hypothesis. Let's do an example. Let's look at a left-sided test. Here's a statistical paradigm. Is the new IQ test too difficult? Imagine that you are a psychologist who just developed a new intelligence test. Your goal is to develop your test as an alternative to the much maligned class of pre-existing IQ tests, of which there are many. You present the test to several colleagues for review, and the majority of members on the review committee seem to feel that the test is too difficult. You believe that their position on the difficulty of the test is political rather than substantive, so you set out to formally test whether the test is too difficult. You decide to use the 5% significance level because this is standard in psychology and sociologic research. Eventually, you will administer the test to what you hope is a random sample of 35 individuals. Now, since IQ tests are designed to have a population mean of 100 and a standard deviation of 15, you begin by estimating the population mean by using the sample mean. If the test really is too difficult, the average score will be significantly lower than 100. Recall that a significant result is one where the null hypothesis has been rejected at the appropriate level of significance. Accordingly, the hypotheses for this problem are as follows. The null hypothesis is that the population mean, also known as the expected value, is what it should be, which for IQ scores is exactly 100. And the alternative hypothesis states that the expected value or population mean, they mean the same thing, is too low, meaning it's less than 100. And here X simply represents the IQ score on your new test. Okay. Eventually, we're going to have to get some data to do this. So eventually, your graduate student analyzes the data and observes a mean of 97.211. Now, obviously, 97.211 is mathematically lower than 100. It's lower. It is. 97.211 is lower than 100, but the relevant question here is whether it is significantly lower than 100. In order to make this example as simple as possible, let us assume that the standard deviation is 15, like it should be for IQ tests. Now, this assumption may not be realistic, but we will embrace it in order to make this example as simple as possible. We will now put this whole scenario into symbolic formalism of the hypothesis testing paradigm, and we will perform our hypothesis test. all this wording will be replaced by something very simple. Look at this. All these words. We'll let X represent the test score on your new IQ test. The null hypothesis is that the population mean is equal to 100. The alternative hypothesis is that the population mean is less than 100. Significance level we set to 5% because that's given in the problem, but that's also culturally accepted. Just culture. It's just what we do. Is there a good reason for it? No. Is it arbitrary? Yes. But that's what our culture has accepted. Now, this is a left-sided test because this inequality symbol, namely the less than symbol, what direction does it point? It points to the left. Okay, so the data is that the sample mean based upon 35 observations, I put the little 35 as a subscript just to make it easy for the eye to see, was observed to be 97.211. We state our assumptions. X has to be normal, otherwise this math won't work. And we've made it to be a simple stats 1 problem by letting the standard deviation be equal to 15, as it should be for an IQ test. Okay, simple enough. The next thing we're going to do is we're going to perform the test. And so we will standardize the sample mean, assuming the null hypothesis is true. Now that we have stated the hypotheses, the significance level, and the assumptions, we can perform our test. Our test is based upon standardizing the sample mean, assuming that the null hypothesis is true. That is, that the expected value, also known as the population mean, is 100, which it should be for IQ scores. Under this assumption, we take the observed mean, we subtract the hypothesized mean, and we divide by the standard error of the mean, which is the population standard deviation divided by the square root of the sample size. And we plug this into the calculator. Now, once we plug this into the calculator, we get an observed value for the z-score. Let's see if we can figure out what that is. Now, we need something to compare that to. So we need a left-tailed critical value. That's what we need. We need a left-tailed critical value. And if we're going to do this at the 5% significance level, then we are going to use the 5th percentile. Okay? So if we look up at that table in the back of the book and we find the 5th percentile of the standard normal distribution, you see we get a value of negative 1.645 as our critical value. Okay, we have that. We now have to decide whether or not to reject the null hypothesis. So how do we do this? Let's just make a little table and just put it all in one thing, or a little diagram. You know, however we're going to do it is fine. If you draw a little diagram like this in a class where your professor wants you to show all your work and, you know, really wants to see what you're doing to give like partial credit and all that, you put your z-score of negative 1.10 over here. You put the critical value that you got from the table over here. And you show that This is where you reject the null hypothesis. Anything less than or equal to negative 1.645. And this region over here, anything greater than negative 1.645, is where you fail to reject the null hypothesis. And some statisticians will say accept the null hypothesis. Whether you say fail to reject or whether you say accept, that depends on your individual professor. I use both to expose my students to the difference. Now, if you look at this negative 1.10, you see that it does not fall in the rejection region. That's what it's called, a rejection region. So we do not reject the null hypothesis. In fact, we fail to reject the null hypothesis, which some people would say is the same as accepting the null hypothesis. We have a critical value of negative 1.645. This test statistic is not less than or equal to this critical value. So we cannot reject the null hypothesis. And we must conclude that the test is not too difficult at the 5% significance level. So we have something very important here. This illustrates that although the observed average is mathematically less than 100, the difference is not statistically significant. And with that, our example comes to a close. And this is Dr. J. Lee Noose for College Statistics.